Alright, so today we're going to pick back up with evaluating limits analytically or algebraically. Here we're going to deal with some special trig limits. Specifically, we're going to deal with sine x over x as x goes to 0, and then also 1 minus cosine of x over x as x goes to 0. I've already gone ahead and done the two graphs, so you guys didn't have to suffer the consequences of watching me do them on the video. But kind of the big takeaways, of course, they're going to be undefined at the on the y-axis because you can't plug in 0 when you have an x on the bottom. But also, let's think like this function, which is sine of x over x. If you were to actually type that in, make sure it's in radian mode. If you were to actually type that into your calculator, you would look like this, which looks more like a cosine. Remember, cosine starts at the top and then goes through its period. Sine starts in the middle and then goes up through its period. So the equation that has sine has the graph that looks more like cosine, and then the equation that has cosine has the graph that looks like sine. So it's a little bit switched. Of course, you still have the holes for the y-intercepts, and then also these are going to go through dampened oscillation. Like this hill goes up to 1, but then this one doesn't quite go to -1. And then that hill is going to be a little bit smaller. And then that next one, right? Since the denominator, right, the bigger you are, the farther away from the from the y-axis you get. Like over here, x is 5. So dividing by 5, okay, it's not huge, but when you take some number, remember this is always going to be some number between -1 and 1. So when I take some small number between -1 and 1, if I were to divide it by 5, right, you shrink it. But then as you move farther away from the y-axis, like here you're like x equals 10. Then here you have like x equals 100, right? And the farther you get, either negative or positive, the farther you get away from the y-axis, the bigger the denominator is going to get, which means the smaller the fraction overall is going to be. So dividing by x kind of causes that little dampened feature and then also kind of flips it. And so that the equation, instead of it being sine, is actually a cosine. That dampens. And then this 1 minus cosine, it looks like a sine graph, except it dampens. Right, so let's look at this. Right, here I've got the limit. Here I changed it to thetas instead of x. If you don't like theta, change it to x. It's literally the same thing. But what do we think the limit as x goes to 0 of sine x over x equals? Well, here's 0. That's my target. It looks like I'm approaching the same thing from the left as I am from the right. That point's undefined, but it doesn't matter. That point is supposed to be at a height of 1. That's where that empty dot is. So the limit of sine of x over x is 1. So coming down here, if you have sine of theta over theta, and then theta goes to 0, that limit is going to be 1. And then the other one, here's the graph. We can see as I approach 0 from the left, and then as I approach 0 from the right, you're both approaching the origin, so then that limit is going to end up being 0. So if you have 1 minus cosine of stuff over stuff, if those two things match and that stuff goes to 0, the limit overall is going to be 0. Right, so here it's written with thetas instead of x's just to represent, like, it doesn't always have to be x's. You may see stuff where it's like 5x, or you may see stuff where it's a 3x or a 2x. In general, if you have sine of something over something, and if those two things match and they both go to 0, then that limit of sine of something over something is going to go to 1. And then here, same thing, right? This theta just represents anything, right? It's a variable. As long as the stuff inside of the trig matches the denominator and that stuff goes to 0, these limits are going to work. Now, an interesting note here, if this limit is true, then you could think about multiplying the theta over, and then you could think about dividing the sine over, right? So if I divide this by sine, you'd have 1. So if you have this ratio with a limit of 1, the reciprocal ratio will also be 1. So the limit, as stuff goes to 0, of stuff over sine of stuff, that's also going to be 1. Right? It's really pretty nice. It doesn't matter if the sign is on the top or if the sign is on the bottom. All you have to do is check what's inside of the trig versus what's in that other layer. And if those two things match, then the sine is going to end up giving you this overall limit of 1. The cosine, the 1 minus cosine over the theta, that's going to be 0. And the reciprocal of 0 doesn't work, right? You can't divide by 0. But this one's nice because the sine could be on the top or on the bottom. The cosine one's a little bit more specific, only works on the top, and if it's 1 minus. Okay, so let's utilize these two facts, and then let's answer these questions. These can be a little bit weird at first, but once you kind of get hang of them, they're pretty okay. So here we go, first example, limit sine of 5x over 5x as x goes to 0. First thing you'd have to check, is x going to 0? Yes, that's going to happen on all these questions. I wouldn't be that mean to you. And then you have to look, what's inside of the trig, 5x? Does that match what's in the denominator? Yes, it does, right? It doesn't always have to be x's. This theta represents anything. So as long as this matches, that limit is going to be 1. That could be a 15x and then a 15x, or that could be a negative 70x and then a negative 70x. As long as the stuff inside the trig matches the chunk in the denominator, that limit for the sine is going to be 1. Now the next one, you see I've got a 5x inside, and then I've got a 4x on the bottom. And 5 and 4 are not the same thing. So this one's not going to be 1. You're going to have to do a little bit of witchcraft in order to get this answer. But before we get to the witchcraft, let's just take this and let's just kind of split it up into some different groupings, right? I'm going to keep, how about this 4, right? That 4 on the bottom, I'm just going to kind of break it out. And I'm going to have a 1/4. And then let's see, I have the sine of 5x over x. So I'm just kind of splitting it up. I'm basically just taking this 4 into its own little group because I didn't really want the 4 to go with the sine chunks, right? Because it didn't match. So here I haven't done anything. I just regrouped it, right? But mathematically it's the exact same thing. Now let's think. What number do I really want to be here? Well, since that's a 5x, I need this to be a 5x. So check it out. We are just going to put a 5 in the denominator. Why am I doing that? Because I know, like, hey, now that that chunk matches the stuff inside of the sine, I know the limit of that piece overall is going to be 1. But if I put this 5 in the denominator, you're changing the value of this expression. So I'm going to have to keep it balanced, right? If I put a 5 in the bottom, I'm going to have to keep it balanced and also put a 5 in the top. So I kind of broke it up and I grouped it in a way that was nice and convenient for me. Then I fixed the group with the sign, right? I put this number in. That means I also had to put another number in to keep it balanced. And now I can go through and I can take this limit. The limit of 1/4 is 1/4. The limit of this chunk is 1. And then the limit of 5 is just 5. So look, we end up getting 5/4, and that's the answer. So a little bit weird, split it up, and then regroup it. Let's do the next one too. Here I have the limit as x is going to 0. I'm just going to leave this 5 out in the front. I have the sine of 2x, and then I have the sine of 3x. So I've kind of just split up the different things that we began with. I don't want those two things to be together. I want one of them in the top and the other one in the bottom. Remember, it doesn't matter if it's in the top or in the bottom. That's okay. Then I just took this extra 5. All right, so let's think. Since this is sine of 2x, I would really need this to be a 2x in the denominator. So I put this 2 in, and then I put this x in, right? Keep track of that. And then in the numerator for this piece, since I have sine of 3x in the bottom, I need this to be a 3x in the top. So I put this in, and then I put this in. Now let's make sure we're going to keep everything balanced, right? Let's check the x's first. I put one x in the bottom, I put another x in the top. Those are already balancing each other out, so I do not need any other x's. I put one in the bottom, one on the top, so I'm already good. Okay, I'm back. Sorry, I had to drink water. My throat is attacking me. Alright, so we put the x in the bottom, the x in the top. Those are good. They cancel. Now remember, I had put this 2 in the bottom, so I know I'm going to need to put a 2 in the top. I had also put this 3 in the top, so to counterbalance that, I need a 3 in the bottom, right? So you kind of break it up and you kind of just create these really convenient clusters for yourself, making sure to keep it balanced as you go, and then you can just evaluate the limit for each piece. So I have the 5, the limit of this chunk, since the 2x match, it's going to be 1. The limit of this chunk is going to be 1. And then you have the 2/3. So then for this answer, you're going to end up getting 10/3. All right, and let's go ahead and look at a little easy rule. Let's go back up to the top. Think about just the coefficients, just the numbers that you can see. If I have x and x, right? Really you have a coefficient out here, then you have a coefficient here and here, right? There's 3 numbers you need to be looking at. Let's see, 1 times 1 divided by 1 gives you 1. How wonderful. Let's look at the first example we did. 1 times 5 divided by 5. Well, 5 divided by 5. Oh, look at that. That's also 1. What about the second one? I had 1 times 5 divided by 4. Okay, so literally 5/4 was the answer. Okay, the next one was even harder. Surely that method's not going to work. 5 times 2 over 3. Oh gosh, I guess it does work, right? Now that trick only works for the ones that are specifically only the sign clusters, right? You should be able to just look at this question and in 2 seconds be able to tell me what the answer is. But you should hopefully also understand the math that's going on behind the scenes, right? But if you've got something like this where you've got other chunks that are not sine, and if you've got other chunks that are cosines, that trick isn't going to work. But if it's strictly the signs, and if you're only using that one sign property, then yeah, you can kind of just look at the numbers and get the answer. All right, moving on. For the next one, what you'd want to do is actually split it up. This one seemed like it was going to be hard, because you're like 2x plus sine of x over x. That's a little bit weird. That's okay. Don't forget your rules, right? You could split it up. Take the denominator for each part and then use your limit properties to split it up. Now here the x's will cancel. The limit as x goes to 0 of 2, that's just 2. Right? The limit of a constant is that same constant. And then the limit of sine x over x, that was 1. So if your parents ask what you did in calculus today, you can tell them with a whole lot of pride that you did 2 plus 1, right? That's the computational math that was in this example. Now you had to know some algebra, right? Like it's possible for me to split that stuff up, and you had to know this little property that this limit gives you 1. But then the only math that you ended up doing was 2 plus 1. And a lot of the questions in my class this year, and then also on the AP exam, they're not always going to be 2 plus 1 easy. But a lot of them end up being fairly simple as far as the computational work you have to do. But there's a lot of algebra that goes on behind the scenes. There's a lot of just properties and general know-how that you need to know. But the actual work that you do sometimes is very, very, very easy. 2 plus 1 in calculus today. Yeah, pretty easy. All right, next one. I think this one matches a question on the homework, so you definitely will probably want to come back to this. There's nothing you can do right now. Remember, the property is 1 minus cosine on the top, and then having an x in the bottom, right? You don't have anything that deals with the 1 minus cosine in the bottom. But the strategy you could use here is to actually use the conjugate, and using the conjugate is going to help. So I'm going to do 1 plus cosine, 1 plus cosine. Remember, the non-conjugates, you're going to just leave them factored. And then the conjugates, you're going to multiply them out. So 1 times 1 is 1. Then you'd have a plus cosine and a minus cosine. Those would cancel. And then you're going to have a minus cosine squared. Let's see, does anyone remember what 1 minus cosine squared is? We talked about it when we did the trig stuff in that pre-cal review. I'm asking questions like someone's going to be able to answer. Okay, just bad habits. 1 minus cosine squared is a Pythagorean identity, and that's actually the same thing as sine squared. Right, so that one seemed a little bit weird, but because we used the conjugate and then I multiplied it out and I got this Pythagorean substitution, now I can go ahead and split it up even more. I've got the limit still as x is going to 0. I'm going to take one of these x's and one of these sines. Then I'm going to take the second x and the second sine. And then that chunk is still just left over, so I have 1 plus cosine of x. And then we are ready for this answer, right? The limit of this chunk was 1. The limit of this chunk was 1. Let's see, that's 1. Let's see, plug it in. You're plugging in the x value is 0. The cosine of 0 is 1. And then, so you have 1 times 2. So the answer ends up being 2, right? So on that question, you needed a 1 plus 1. Oh my gosh, that's really challenging. Now, there was a lot of math behind the scenes there, but the computational part was pretty easy. Okay, the next one, we have x cosecant x. Oh my gosh, that looks like a nightmare. But just remember, right, you don't really want to work with cosecants and secants and cotangents. You'd much rather work with sines and cosines, and maybe if you're having like a really bad day, maybe a tangent. But here, instead of the cosecant, I'm just going to use the reciprocal function. And cosecant is the same thing as 1 over sine. All right, it's just a very basic trig fact. And then you could just regroup those, right? Instead of having x times this chunk, you could just regroup them and have x over sine of x. And then look, like this question is hardly any work at all. The answer is 1. It's just one of the basic facts that we learned and we've been dealing with for this whole page. But you had to recognize that the cosecant is kind of a distractor. It's there to trick you and to get you. But if you just remember that how you to put it back in terms of sines and cosines, then it ends up being a very, very, very easy question. Okay, now this last one, let's go for it. This last one's even kind of a trick, because there's nothing really you can do algebraically. But don't forget, like the first thing, all of these, if you were to try to plug them in, right? This one would have cosecant of 0 gives you an error. But all the rest of them, right, if you try to plug it in like this or like this, all of them are going to end up giving you the 0 over 0, so that indeterminate form. I just didn't ever bother doing the work for you earlier. But here, there's no strategy, really. Like, there's no conjugate to do. There's nothing you could really change it with. The reason why, right, if you're searching your brain, you're like, well, I don't know what to do. It's because it's easy. You actually, you just need to direct evaluate. Can't speak. All you need to do is just direct evaluate. Just plug it in, right? Plug in the x as 0. So we've got 0 over cosine of 0. Cosine of 0, we just did it on the previous question, right? Or up here, cosine of 0, that's the right side of the unit circle. Cosine of 0 is 1. And then 0 divided by 1 is 0. So that answer gives you 0. It has nothing to do with this property up here, right? All that was a simple direct evaluation, and then 0 divided by 1 is 0.